welcome you all to the lecture series of Detailed Electronics KOE 039/049. Myself Dr. Krishanu Kundu. Today we will be discussing on combinational circuits, and the most two important combinational circuits we are going to discuss in today's lecture is full adder, half adder and subtractor, half subtractor and full subtractor. So, let us proceed. This is the today's table of content. We will be going to discuss first the introduction to the combinational circuits, then we will discuss the design of half adder as well as full adder, then we will discuss about the designing of half subtractor and full subtractor. So, what are basically combinational circuits? Combinational circuit is a circuit in which we combine the different gates in the circuit and whose output depends only on present input. The output changes as well as we are changing the inputs. The combinational circuit do not use any memory. The combinational circuit can have n number of inputs and m number of outputs. In the diagram itself you can see there are n input variables and there are m output variables. Next, classification of combinational circuit. Combinational circuits can be categorized in three parts, that is for arithmetic and logical functions, for solving arithmetic and logical functions, for data transmission and for code converters. These are the examples of combinational circuits which are performing the arithmetic and logical functions like adders, subtractors, comparators and PLDs, program logic devices. Then data transmission, the examples of combinational circuits are multiplexer, demultiplexers, encoders and decoders. And the examples of code converters such as binary code converter, BCD code converter, 7 segment code converter. Next, now today we will discuss half adder. So, half adder is a very common example of combinational circuit. It is a combinational logic circuit with 2 inputs and 2 outputs. The half adder circuit is designed to add 2 single bit numbers A and B. It is the basic building block of addition of 2 single bit numbers. Already we have discussed the logical OR operation, binary addition, already we have discussed in previous lectures. So, the concept of binary addition we are using here. Okay. So, let us see, it is a block diagram of half adder. Here we are having 2 inputs A and B and 2 outputs sum and carry. Whenever we are going to add, suppose we know, suppose we are having A and B. So, if we do binary addition, so 2 inputs, so 4 combinations 0 0, 0 1, 1 0 and 1 1. So, if we add 0 0 according to binary addition rules, so 0 0 sum will be 0, carry will be 0. If we add 0 and 1, sum will be 1 and carry will be 0. Similarly, if we add 1 and 0, sum will be 1 and carry will be 0. But the most important part is when you are adding 2 ones. So, 1 plus 1 in binary addition, sum will be 0 and carry will be 1. So, this is the truth table of half adder circuit. Now, we are going to implement this in Boolean expression and then we will design the half adder circuit. So, from this we have got the sum is equal to main terms small m, this is 0, 1, 2 and 3. So, sum is 1 and 2 and carry is summation small m only here. So, 3, this is nothing but 3. So, now we will do the K map for this. So, here already we are having the slide, again I am doing the thing. See, I am having the truth table 0 0 sum and 0 and carry 0, for 0 1 sum 1 carry 0, for 1 0 we are having sum 1 carry 0 and for 1 1 we are having sum 0 carry 1. So, this thing we are going to implement using K map. So, here 2 variables A and B. So, here we will write A and B 0 1 0 1. This is nothing but B bar, this is B, this is A bar, this is A. If you are having any doubt of K map, you can refer previous videos. So, here this is for sum, this K map will be for sum and this K map for carry, this is C, this is S. So, first of all we are just making the format of K map for 2 variable K map. So, this is 0 1, this is 0 1. Okay. So, now we will write the positions. So, this is 0 1 2 3, this is 0 1 2 3. So, in the previous slide I have already mentioned the sum is for minterms SOP form. Okay. So, 1 and 2 and this is for carry is for only 3 minterm 3. So, here we will write. So, here 1 and 2 and for carry only here 1 1. Okay. So, let us solve the K map. So, this is nothing but no grouping is there, we cannot group anyone. So, here the value will be A B bar and this will be A bar B. So, the equation for sum will be A bar B plus A B bar, got it. And for carry, this is for carry the Boolean expression will be only this. So, this is nothing but A B, got it. We have got 2 Boolean expression, for sum we have got A bar B plus A B bar and for carry we are having A B. So, now it is very easy to design the diagram. So, A and B, and one more thing, this is nothing but the XOR gate, okay. A B bar plus A bar B, okay. Sorry, here I have written something wrong, this is A B bar and A bar B, A B bar and A bar B, okay. So, now this is the XOR gate, okay, and this is for sum, this is output for sum, and for carry we are having one AND gate, this is A B. So, this is for carry. So, this is the circuit design for half adder circuit. Now, let us go to full adder. The same concept of half adder will be used in full adder, but here we can add 3 bits. Previously we can add only 2 bits, here we can add 3 bits. So, what is the definition of full adder? Full adder is developed to overcome the drawback of half adder circuit. It can add 2 1 bit numbers A and B and 1 carry C in. The full adder is a 3 input and 2 output combination circuit. Okay. So, here we are having 3 inputs A, B and C in, and here 2 outputs sum and C out. Okay. So, just here you have to very particular about the binary addition. So, let us check here 0 plus 0, 0, 0 plus 0, 0. So, sum 0 carry 0. Okay. For next one 0 plus 0, 0, 0 plus 1 sum 1 carry 0. Then 0 1 0 we are having 0 plus 1 sum will be 1 and 1 plus 0 carry will be 0. Like that we will format the truth table of truth table for full adder circuit, and ultimately the equation for sum will be as summation of min terms 1, 2, 4, 7. For 1, 2, 4 and 7 will be getting sum as 1. So, the equation will be 1, 2, 4 and 7. Like that for C out we will be having the equation as 3, 5, 6, 7, summation m 3, 5, 6 and 7. Okay. Clearly, you have to just remember the last point I am giving when all are 1. So, 1 plus 1 what will be there? Sum 0 carry 1. So, already carry will be 1 here and sum is 0. So, 0 plus 1 sum will be 1 and carry is 0. So, this is the most last one, the last combination when we will adding A, B and C in all 3 1, then in that case this will be the combination. Okay. This is very important. So, now we will be going to draw the K map for the full adder circuit. So, already we are having for sum we are having, for sum we are having summation m 1, 2, 4 and 7, and for carry we are having summation m 3, 5, 6 and 7. So, this is for 3 variable K map, because the maximum value is 7. So, we have to go for 3 variable, and already we are having 3 inputs A, B and C in. Okay. So, that it will be a 3 variable K map. So, just draw the diagram. So, we are having A and this is B and C in, okay, and here also A, B and C in. So, the thing is 0 0, 0 1, 1 1, 1 0. You remember this is gray code format using in K map. So, 0 0, 0 1, 1 1 and 1 0, and this will be 0 and 1. Similarly, this is 0 0, 0 1, 1 1 and 1 0, and this is 0 and 1. So, the numbering will be 0 1 3 2 4 5 7 6. Already we have discussed this numbering pattern, gray code numbering pattern in previous lectures. You can follow that. Now, this is again the numbering is 0 1 3 2 4 5 7 and 6. Okay. Now, we will put the values of 1. So, for here 1, 2, 4 and 7, okay, and for 3, 5, 6, 7, 3, 5, 7 and 6. So, now we have all put the ones in the K map. Now, we will do the minimization part. Okay. So, minimization part, see, from this we cannot group any ones, because no adjacent ones are there. So, all will be individual, this will be individual, this will be individual, this will be individual and this will be individual. So, this is nothing but we will get the value of sum as, after solving the K map, the value of sum will be A B C in plus A B bar C in bar plus A bar B C in bar and A bar B bar C in. How it is coming? See, this is nothing but A B bar C in bar, means this one is this grouping. Okay. Now, A B C, this is this one grouping. Now, A bar B C in bar. So, this one, this grouping, and A bar B bar C in. So, this grouping. Okay. If you are having any doubts of K map, just refer the previous lectures, will be very easily can understand the grouping. So, now we have got the expression for sum and for expression of carry. So, now here we can having the, we can group the one. See, one grouping is this, one grouping is this and one grouping is this. 3 groups of ones we are having. So, what will be the values? So, the values of carry will be, if we group is this one, this is B C in, this is nothing but B C in, this one is A, this is A and C in, A and C in, and last one is, this one is B and C in. Okay. This is B in, B and C in. So, here we are having, sorry, this is nothing but B C in, this is already B C in we have got, this is nothing, this is actually B C in we have got A C in, and this will be A B, A and B. Okay, right. So, this is the equation for carry, right, got it. So, now if we solve this into a format, this is the final expression we have got and this is the final expression we have got for carry. So, if we solve it and we will design using logic gates, so this will be the final full adder circuit. Okay. This will be the for sum and this will for carry. Okay. Next, Next we will do for half subtractor. So, what is half subtractor? Half subtractor is a combination of circuit with 2 inputs and 2 outputs, and difference and borrow, it produces the difference between 2 binary number bits, the input and the produces an output to indicate that if one has been borrowed in the subtraction A minus B, A is called the minuend bit and B is called subtrahend bit. Already binary subtraction we have covered in previous lectures. So, that rule we are using. So, here 2 inputs A and B. So, if we make subtraction, binary subtraction, 0 minus 0, the difference will be 0 and borrow will be 0. Then 1 0, borrow, difference will be 1, borrow 0, and 1 minus 1, difference will be 0 and borrow 0. The most important point is this one. We are doing 0 minus 1 means bigger number is being subtracted from a smaller number. In that case, the difference and borrow both will be 1. This thing you have to remember, this is the most important part of half subtractor. So, now this truth table will make transform into K map and we will solve the minimization problem. So, here 2 variables A and B. So, this is 0 1 0 1, though the format numbering format 0 1 2 and 3. So, here also for this is for difference, this is difference D, this is actually D difference, and for borrow we are having again one K map. So, this is A and B 0 1. So, the format is 0 1 2 and 3. Okay. So, first of all we will make the difference one. So, here just follow this column. So, we are having ones for what? For 1 and 3. So, we are having 1 and 2, we are having 1 for this 1 and 2. So, it will be written as difference will be summation small m 1 2. So, just the K map will be, we will put 1 and 1 here. So, any grouping is possible? No, no adjacent ones. So, no grouping is possible. So, this will be an individual, this will be an individual. So, it will be as difference will be nothing but this one is nothing but A B bar and this is nothing but A bar B. Okay. So, the Boolean expression for D difference is A B bar plus A bar B, and for this is for borrow only 1, this column if we cover this column. So, we are having only 1 here for 1. So, here we will go put it here. So, no grouping, only one individual. So, this is nothing but A bar B. So, borrow will be A bar B. Got it? Clear? So, we have got 2 Boolean expression, one for difference, one for borrow. So, we will now draw the diagram half subtractor circuit. So, this is the actually we have got D is equal to A bar B plus A B bar, this is nothing but an XOR gate. So, here we have made a XOR gate and this is nothing but borrow is equal to A bar B, borrow we have got A bar B, A bar B. So, here we have used an inverter. So, this output will be A bar and this is B. So, one AND gate is there. So, output will be A bar B. Is it clear? The half subtractor circuit. Okay. Now, we will go further for full subtractor. So, the disadvantage of a half subtractor is that it can only subtract 2 bit numbers. So, to overcome that we use full subtractor, like half adder can be replaced by full adder. So, here we are replacing half subtractor with full subtractor. So, the full subtractor is a combination circuit with 3 inputs A, B, B in and 2 output D and B naught. So, here just this is nothing but D and this is B naught. Here I am doing this is 3 inputs A, B and B in, okay, A, B and B in, and this is D and B naught, correct, and there will be two output D and B naught, right. A is the minuend, B is the subtrahend and B in the borrow produced by the previous stage. What is D is the difference output and B naught is the borrow output. So, let us check the truth table first and then we will do the K map. So, here 0 minus 0, difference is 0, borrow is 0, 0 minus 0, difference is 0, borrow is 0. So, this is correct. For this one 0 0, borrow difference 0, borrow 0, 0 1, just go to the previous, here 0 1, difference will be 1, borrow will be 1. So, here difference is also 1 and borrow is also 1. Okay. Next 0 comma 1. So, here difference will be 1 and borrow will be also 1 and difference 1, 1 minus 0. So, already difference will be 1 only, it will be remain as 1. Okay. Next 0 comma 1. So, difference will be 1 and borrow will be 1. Now, 1 minus 1, 1 minus 1. So, it will be 0, but borrow will be remain 1. So, this is the case 0 and 1. Here 1 minus 0, difference 0, sorry difference 1, borrow 0 and 1 minus 0, the difference will be remain as 1 and borrow will be remain as 0. Okay. Next 1 minus 1, difference will be 0, borrow 0 and here 0 minus 0. So, difference will be 0 and borrow will be 0. Last case here 1 minus 1. So, it will be coming as 0, difference will be 0 and borrow will be 0, but next again we have to minus 1. So, if we minus 1 then it will be coming as difference will be 1 and borrow will be coming as 1. So, this is the most important part, here we will be getting difference as 1 and borrow will be 1. Got it? Okay. So, this truth table is very important for full subtractor circuit. Now, we will be doing the K map for this. So, here we are having 3 variables A and B in, okay, A, B and B in. So, just we will put the 0 0 0 1 1 1 1 0 and 0 1, the numbering format 0 1 3 2 4 5 7 and 6. So, here we will check this column, for which case we are getting 1. Let us check, we are getting 1 for decimal part is 0 1 2 3 4 5 6 and 7. So, 1 for 1, second one for 2, 4 and for 7. So, we will be having the difference will be summation small m 1, 2, 4 and 7, okay. And for borrow we will having for 1, 2, 3 and 7, 1, 2, 3 and 7. So, the borrow will be B naught will be summation m 1, 2, 3 and 7. Got it? So, now we will just group this. So, this grouping will be for 1 to 1, 2, 4 and 7. So, no adjacent ones are there. So, what we can do? If no adjacent one are there, so all will be individual. So, we will get the equation, like this. The ultimate, this is nothing but same as you can check, this is same like the full adder, like this, same combination. Okay. So, we will write that value. So, it will be coming as full adder D will be, write down, D will be A B B in, A B B in plus A B bar, A B bar B in bar plus A bar B, A bar B B in bar plus A bar, B bar, A bar, B R, B bar, B in. So, this is the minimized form of K map, and for borrow we will be having B naught will be, if we do the thing. So, if we solve it, so we will be having A bar B, this 1 2 3 7. If we solve the K map for this, we will be getting as minimized expression A bar B plus A bar B in plus B B in. Okay. So, this will be the format for borrow. So, now just look at the full subtractor circuit. So, already we have seen this is the difference and this is the borrow. So, we have drawn the circuit for full subtractor. Okay, clear? Next, sometimes they can be asked you to design half adder circuit or full adder circuit using universal gates like NAND and NOR. So, if we are going to implement half adder circuit using NAND gates, so what is the formula for a half adder? Just go to the half adder circuit. See, the concept for half adder is this one, sum will be A XOR B and the carry will be A B. So, this thing we have to implement using NAND gates. Okay. So, just check out, see the half adder circuit sum will be A XOR B and carry will be A B. So, this thing we have to implement using NAND gate. So, here 2 inputs. So, now first we have we are using 5 NAND gates 1, 2, 3, 4 and 5. So, what will be the output for first NAND gate? Here it is coming A and B. So, it will be A B whole bar, A dot B whole bar. So, now this is going to a NAND gate 2 and this point is going to NAND gate 3. So, the output will be NAND gate 2 will be A dot B bar whole bar and here B dot A dot B whole bar whole bar. So, now we are putting this into the 5th NAND gate. So, the output will be this one and this is by De Morgan's theorem, this is nothing but A XOR B. Okay. So, now and here this is for sum, we have got this as sum, and for carry if I am putting, so this is coming as A dot B bar, we are putting in using a inverter, this is nothing but inverter in terms of NAND gate. So, we have put it and we have got A dot B double bar. So, we have got the carry as A dot B. Like that you can implement full adder, half subtractor, full subtractor using NAND and NOR gates. Okay. So, these are the gates we have using logic gates, we have implemented half adder circuit, then we have implemented full adder circuit, then we have implement the half subtractor and full subtractor circuit. Thank you.